Good evening, everybody. Welcome to Turfgrass Epistemology. My name is TravisShaddox. Thanks so much for joining me tonight. This channel explores how we know what we know about turfgrass science. We explore the scientific literature and try to provide a little bit of evidence to support our beliefs and our management practices. This month and maybe even next month, we've been going over soil testing. And we're going to be going over soil testing again tonight. So real quick, the next week, the member stream is, one second. Yeah, I'm not, hang on. Next week, we have a members only stream on Monday morning, and then we're doing video streams on Tuesday morning that are open to the public. And that'll be like a video commentary time on Tuesday morning. And then we have the Thursday night show like tonight for open to the public. So the show is also broadcast on a podcast. So in 24, 48 hours, this episode will be on podcast, all your podcast platforms. You may listen to that. And what else? If you want to consult with me about any of your turfgrass related issues, you can go to calendly.com/TravisShaddox and sign up for whatever Calendly, appointment and time that's available there. So hopefully we get through tonight. There's all sorts of stuff going on. And for some reason, I get this question a lot about signing up as a member. I don't think you can sign up as a member on a phone. I think you have to be on a desktop to do that. So if you're having difficulty finding the sign up button, you might want to check the desktop or like a iPad or something. Because I think it won't show up on a phone. You have to go to the desktop. That's all I got. Okay, so now let me start. So we're going to be going over base cation saturation, and we're going to show a couple of PDFs and soil samples before we get started here, or as we get started here, just so everybody understands what we're talking about. So the base cation saturation, what is it? What does it look like? So we're all on the same page. This is a soil test report. You'll see various variables and data on here. The potassium, magnesium, calcium, sodium, all these things you're used to, soil pH, these are all things that are useful. The base cation saturation is over here on this particular report over on the right, and it says % cation saturation. This is an indication or a measurement of the percentage of the cation exchange locations that are occupied by these various cations. And this is what we've been talking about. This is what we're going to talk about, just so everybody is on the same page. Here's another example of a report that you may come across. This report is from Logan Labs, and you'll see some of the information on here is very similar, very common. You'll see it on other reports, organic matter percentages and pH of the soil sample. Here's the CEC, sample depth in inches. And you go through here and you'll see this. Now, what I want to point out here is that the area that we're going to talk about tonight is the base cation saturation. This is actually down here below it, below the values, exchangeable cations. And this dark gray area is the area that we want to ignore. We don't really want to use that at all. There's really no evidence to support it. And we're going to be going over that tonight, just so everybody's on the same page. Okay, so if you're unfamiliar with what base cation saturation is, it is the measurement of the base cations, potassium, magnesium, magnesium, calcium, sodium, hydrogen's on there too as well. It's not a base, it's an acidic cation. But they'll measure those, and they'll have a percentage of the exchange sites that are occupied by those ions. And they'll say the percentage needs to be 65% calcium or whatever. And so they're trying to balance the soil. That's what base cation saturation is, soil balancing, okay? All right, so how did we get into this situation where we have on soil test reports around the United States, it used to be all over the place. Nowadays, the land-grant institutions have mostly removed the base cation saturation component of soil tests. You don't see them on every land-grant institution report anymore. Occasionally, you'll find one. But you'll see them a lot on commercial labs. They'll include base cation saturation on commercial labs. And the question is, how do we even get here? And this paper is going to go over how we got here and basically how did this whole mess start and the challenges with it. That's the purpose of this paper tonight. This was written by some Aussies, I guess. And maybe somebody from, some Aussies from down under. We have one or two people listening in Australia. I've noticed the podcast, it gets downloaded in Australia as well. So this is a little article written by some of their brothers and sisters down there and down under. So the paper is called A Review of the Use of the Basic Cation Saturation Ratio and the Ideal Soil by Kopetke and Minzy. This was published in 2007 in Soil Science Society of America journal. So this is one of our top tier journals from the Tri Society, Soil Science Society of America, and they published this in 2007. You can go look at the abstract. I don't know if it's open access or not, but you can go read the abstract, or you can become a member of the Tri Society and download this and other articles for free. Well, with your membership. Okay, here we go. The aim of most soil analytical tests is to provide a measure of the phytoavailability of nutrients, quantity, or buffering capacity. I'm not exactly sure how this is all happening, but it's okay. Or buffering capacity. The information gathered from soil testing is often used to guide fertilization practices. Of particular interest to this review are the cations calcium, magnesium, and potassium, which in a typical soil are present in the solution phase, but are predominantly absorbed on the soil's exchange complex. While it is typically comparatively easy to measure the soil's exchangeable cations, it is more difficult to relate the analytical data obtained to phytoavailability and plant growth. Soil concentrations of calcium, magnesium, and potassium are generally interpreted using two different methods. That's the Slan method and the base cation saturation method. So for those of you who are unfamiliar with Slan, it's the sufficiency level of available nutrients. That method basically says that the manner in which you should apply or consider applying elements is based upon some critical limit. Okay. So if the critical limit is 20 and your soil test comes back as 30, then it's unlikely that you would actually need to apply it. But if it's 20, it comes back as 5 or 10, then it's likely that you would need to apply that. That's the sufficiency level. The base cation saturation concept is, like I said, balancing all these things out on the exchange site. Okay. According to the sufficiency level concept, there are definable levels of individual nutrients in the soil below which crops will respond to added fertilizer and above which they will probably not. So I just explained all this whole paragraph. Okay, so I'm not going to repeat it. In contrast to the sufficiency level, the concept, base cation saturation concept, also known as mineral balancing or soil balancing, aims to fertilize according to the soil's needs. So if you've ever heard, got to feed the soil, I don't know if I included that in the BS manual or not. But that's definitely a sign you're dealing with a BS artist when they say, you need to fertilize the soil. We're not growing soil. When we start growing soil, then I'll start fertilizing for the soil. We're growing plants. So we need to fertilize the plant. And really all the literature will direct us in that direction. It'll guide us into that direction. Because when we fertilize the soil, when you fertilize the soil, or when you feed the soil, will you end up with acceptable plants? Yes, you will. It'll just be very expensive to do that. Okay. I had to turn on the subscriber only, by the way, just so you guys know. I'll turn it back on maybe later if it works out. Sorry for the subscribers. But anyway, welcome those of you who are joining tonight as subscribers. Okay. So the base cation saturation holds that there is a balanced ratio of basic cations for the soil's cation exchange capacity, and that plant growth will be reduced in the soils that do not contain the cations in the specified ratio. This idea originated largely from the work of Furman Baer and co-workers in New Jersey, who proposed the concept of a soil that they considered was ideal. The absolute amounts of available calcium, potassium, and magnesium are not so important as their relative values. So that's what Baer said in 1951. So in 1945, Baer came and said the ratio should be this. And then in the same year, 45, he said it's not really that important. And then later in 51, he said the absolute amounts of available base cations they're not important as the relative value. So he's going back and forth in the literature. Dr. Baer was. Okay. The ideal soil proposed by Baer was widely promoted by William Albrecht as a balanced soil, particularly through the publication of the Albrecht papers. We're going to go over that tonight. So a large portion of tonight's show, or really almost all of tonight's show, is going to be about Dr. William Albrecht and how he misunderstood what he was measuring, and then how he became indoctrinated and delusional about the value of base count and saturation. While various values have been proposed for the base count saturation ratio, they generally fall within the following approximate ranges of 65 to 85% calcium, 6 to 12% magnesium, and 2 to 5% potassium. While university laboratories almost exclusively use the sufficiency level concept to interpret soil and analytical data, McLean in 1977 suggests that approximately 80% of the samples being tested in the north-central region of the U.S. in the late 1960s were tested in private laboratories and interpreted according to the base count saturation concept. So what the author's doing is building cases. Why is this important to go over? Because a lot of people are using it. This was in the 1960s. Okay. Leibhardt in 1981 estimated that between 80 and 90% of the soils tested in Delaware used base cation saturation. It is estimated that at least 90 to 95% of the soils tested by the turf industry in Australia are currently tested according to the base cation saturation concept. Can you believe that? So down in Australia, 90 to 95% of the turf samples go by base cation saturation ratio. And I know we have some people listening in Australia. I wonder if that's accurate. I wonder if they have the same position. Like, yes, that's very common down here in Australia, that base cation saturation is widely used. And I know, like I said, for those listeners who are down there, I know there's at least 2 or 3 down there. Maybe they can shoot me an email or chat here tonight if they're online. Let us know. Yeah, that's 90-95% seems awful high. That's crazy. Can you imagine 90 or 95% of your soil samples coming in and you're basing it on base count saturation, a system that is known to waste nutrients and be very expensive to use? I mean, my gosh. In a field experiment conducted in Nebraska over a period of 8 years, the cost of purchasing fertilizer according to the recommendations of base count saturation concept was generally double that of when fertilizer was purchased based on the Slan recommendation. This is the Olson 82 paper that I've been talking about so much over the last few episodes. I'll be going over that probably next Thursday, maybe Monday. Double. So Olson in 82 generally always found that the base count saturation was very expensive, much more expensive than the Slan method if you followed it. But in some cases, they found that it was double. So no one's here, and certainly not me, arguing that if you followed base count saturation, or those people might be listening, they're saying, well, this is ridiculous because I do it and I have good turf. No one's arguing, at least I'm not arguing, that you wouldn't have good turf. Okay. McLean clearly showed that in his crops. You're going to have the same growth, the same yield. That's not the argument. The argument is you're going to do so for a lot more money. And in the case of Olson 82, they determined it was double the money per acre. Okay. This paper tonight examines the suitability of base count saturation concept as a method for the interpretation of soil analytical data. That's true. They do that, but these authors do a pretty good job of laying the historical background, and they do a pretty good job of at least glancing over why Dr. Albrecht was incorrect. His own data clearly showed he was incorrect, and we're going to get into that. And it has everything to do with pH. Okay? Research before 1930, it appeared that Lowe, and we've talked about Lowe before in the past, in 1892, was the first to suggest there should be a calcium-magnesium balance. Lowe in May 1901 concluded the best proportion of soluble lime to soluble magnesia for the germination and growth of plants is about a molecular weight of 5-4. Close examination of their own data, however, reveals that several of the species examined, maximum growth was obtained across a wide range of calcium-magnesium ratios. Indeed, Lowe and May reported that of the 5 calcium-magnesium treatments for oat, growth was normal in all except the highest calcium-magnesium ratios. And that's one thing that happens sometimes. I mean, they just misinterpreted the data. They see something or they begin to believe something, and they can't believe the data. It's like flying. I'm not a pilot, but it's like if you're flying an airplane and you're looking at your instruments and you're like, these instruments are saying I'm going in the wrong direction. I'm going the wrong direction. You have to believe the instrument. You trust the instruments. Okay. Just because you think you're going in the right direction, the instruments are normally correct. Okay. It's rare that an instrument would break. And in this case, there are data staring at them in the face, and they just formed the wrong conclusion. They just didn't believe it. And you trust the data as best you can. I mean, as long as it's performed and collected correctly. Lippmann in 1916 reviewed the topic and found that while several researchers had identified optimum calcium-magnesium ratios for various plant species, many weren't able to identify a precisely defined ratio that improved growth, but rather found that growth was maximal across a range of ratios. Interpreting the results of many of these early studies by Lippmann is difficult, however, as soil pH was rarely, if ever, controlled for. Now, in the previous paper I went over, it was, I can't remember the author's, Coleman, I think it was, I can't remember now. But they were adjusting the calcium-magnesium ratios, but they were doing so intentionally without altering the soil pH. That was the objective of their study. Let's not alter the soil pH and just look at the ratios, because they recognized in these early studies, they were altering the calcium-magnesium ratios, but they weren't even recognizing that they were changing the soil pH. Okay? And the indoctrination and the delusion was so strong by Dr. Albrecht that he would even state in his papers, in the Albrecht papers, that plants aren't really affected by soil pH. That's what he said. And the quote is in this paper, and you can pull it up in the Albrecht papers. We're going to get there. Can you imagine listening to a professor, listening to someone, a so-called specialist, and you're at a meeting, whatever the case is, and he gets up to talk about soil fertility, and the first thing he says is, plants aren't really affected that much by soil acidity. I mean, you would just write it off like he doesn't know what he's talking about. And clearly, he would, he's inaccurate. But I think what happened was he was so convinced that calcium-magnesium ratios and balancing was the way to go that he just ignored the data that's staring at him in the face. And we're going to look at his data tonight. We're going to look specifically at Albrecht's data tonight, where he said, oh, acidity's not that important. Meanwhile, his data is right there showing it was extremely important. I think it's just a matter of indoctrination and delusion. It's hard to get out of when you're that far down the rabbit hole of base kind saturation. Indeed, so he says Lippmann is difficult, however, as the soil pH was rarely ever controlled for. Indeed, the addition of lime to increase the calcium-magnesium ratio simultaneously increased soil pH and thereby reduced any growth limitations imposed on the plant by soil acidity, such as that from aluminum or manganese toxicity, and may also have reduced phosphorus deficiency. There's a lot going on when you start throwing the pH way down there low or start moving it way up high from a previously low level. The literature was reviewed again by Moser in 1933, who also conducted his own research on calcium-magnesium ratios. Moser concluded that there was no correlation between calcium-magnesium ratio and crop yield, but rather that yield was dependent on the calcium status of the soil. Indeed, in soils with high magnesium contents, low yields often resulted from calcium deficiency rather than an excess of magnesium. So, even before the ratio, the base concentration ratio nonsense was actually formulated into these ranges, the other non-indoctrinated scientists were looking at this and going, we're not seeing what you're seeing. We're not seeing any of this. All this calcium magnesium stuff from low, when we look at it on these other crops, we're not seeing at all what he's seeing. Okay. It's a shame it continued, actually. During the 1940s, Dr. Baer and co-workers conducted a series of studies in New Jersey agricultural experiment station investigating the growth of alfalfa. In 1945, tentatively, Baer stated that their evidence indicated that for the ideal soil, 65% of the exchangeable complex should be occupied by calcium, 10 by magnesium, 5 by potassium, and 20 by hydrogen. No one really knows how they come up with these ratios, though. And they say that a lot in this paper. How'd they come up with these? We have no idea. Good evening, Mike. Since that publication of these reports by Baer, it has been assumed by many that optimum plant growth will only occur when these ideal conditions are met. This is a huge problem. People think, oh, well, if I'm not balanced, then I'm not going to maximize my growth. That's a major problem. They think it'll only occur if it's balanced. This is despite Baer and coworkers acknowledging that maximum growth will occur across a wide variety of cation ratios. The very person who said it needs to be balanced stated it didn't need to be balanced. Then he came back and said it's more important to be balanced than any, elemental level. It's bizarre. Indeed, Baer and coworkers noted that good growth occurs across a wide range of calcium-potassium ratios. I'm going to show these charts in a minute. A high calcium saturation percentage limits luxury uptake of potassium. Potassium is a much more expensive element than the calcium which it replaces. Now, before I read the next sentence, what he was trying to do, Dr. Baer was trying to do, he was trying to limit the uptake of potassium beyond what the alfalfa actually required, because potassium was expensive back then compared to calcium. So he was just trying to limit the amount of uptake of potassium by alfalfa so that it would remain in the soil so they wouldn't have to apply more and more of it later. Okay, because alfalfa at the time was used what they call luxury consumption of potassium, using more than it needed. So he was trying to limit that because the application of calcium was less expensive than the application of potassium. Okay, that's what he was trying to do, Dr. Baer was. Thus, the application of calcium to reduce potassium uptake was cheaper than applying potassium that would be taken up by the plant in luxury amounts and not used, basically. So that's sort of how this whole mess developed from a calcium-magnesium ratio by low into now we're really looking at all these balancing acts going on. He was just trying to limit the uptake, the unnecessary uptake of one element that was more expensive than calcium by applying calcium. At about the same time that Baer was conducting his investigations, Dr. Albrecht and coworkers were also conducting a series of experiments at the Missouri Agricultural Experiment Station. Much of their research investigated the growth and into fixation of legumes. Albrecht concluded that it is important to maintain a high calcium saturation percentage. Indeed, it was this observation that would eventually form the basis for much of the Albrecht's concept in balanced soil. It would seem, however, that the design and interpretation of the experiments used to demonstrate the need for high calcium saturation were often flawed. Okay, let me make sure this is clear to all the base cation saturation salesmen and customers that are using base cation saturation who don't believe what I'm saying and don't believe the evidence, and they're basically evidence deniers. Okay, make sure this is clear. I'm going to read it again. It would seem that Dr. Albrecht, his conclusions, were flawed because the design and interpretation of his experiments were flawed. Okay, those are pretty strong words. Let's look into it. Okay. Albrecht stated that plants, here it is, right here, the most ridiculous statement probably ever made by a soil scientist is about to be read. Okay. Albrecht later stated that plants are not sensitive to or limited by a particular pH value of the soil, and that nitrogen fixation is related to acidity or pH only, as this represents a decreasing supply of calcium as a plant nutrient. I don't know. I mean, if you said that today in an interview, if you were interviewing for like a faculty position, I don't think you would stand a chance of getting it, because that is the most ridiculously ignorant statement I've ever heard. And it's not as if the evidence refuting that statement came about after Albrecht's time. It was in this literature long before 1940. The influence of soil pH on plant growth is what I mean. Soil pH is probably the most influential soil-related factor on plant growth. And he's saying right here, plants are not sensitive to or limited by a particular pH. It says it right here. Albrecht, 1975. Examination of the data of Albrecht in 1937, however, reveals that nodulation is indeed inhibited by soil acidity. Of his own data, 1937, Albrecht's own data revealed that nodulation is indeed inhibited by soil acidity. Nodulation only occurred when the pH was greater than 5.5, and no nodulation occurred at pHs of 4 or 4.5 or 5 at any calcium concentration level. Let's look at this down here. This is really important to see. So this is a graph from Albrecht's 1937 paper. It's his own data. And we're looking at on the y-axis, number of nodules per 50 plants, and on the x-axis, we're looking at initial pH. And these lines, there's 3 lines on the graph, and these are increasing amounts of calcium that he applied. Okay, so you'll see when more calcium was applied at 6.5, they had greater nodulation. If you want to know millimoles, 0.2 millimoles of calcium, 0.1 millimoles, or 0.05 millimoles. So 0.2 millimoles resulted in the greatest nodulation at 6.5. It resulted in the greatest nodulation at 6 and greatest nodulation at 5.5, but it's going down. All these are declining as the pH declines. And at 5.0, there was no nodulation regardless of the amount of calcium applied. In 4.5, there was no nodulation, and at 4.0, there was no nodulation. This is how this thing got all messed up, because Dr. Albrecht didn't understand what he was looking at, or he was so indoctrinated and delusional, he just didn't want to acknowledge that his own data refuted his position. That's just the reality we're in. I mean, it's not as if they somehow came up with these data from someone else. These are his own data. No, pH has a massive influence on plant growth. And it's right here on this graph. It didn't matter once you got down into the pH ranges where aluminum, manganese toxicities can occur, iron toxicities can occur. It didn't matter how much calcium you applied. The plant was not going to result in any nodulation. Nodulation occurred only above 5.5. So they made a strong statement earlier that his data was often flawed, or his conclusions were often flawed. And here's evidence to support their position. And they made a strong statement, and they provided strong evidence to support it. Similarly, although Albrecht concluded that growth and nodulation improve as calcium saturation percentages increase, soil pH values were not reported for any treatment, and due to the methodology used, any increase in calcium saturation would have undoubtedly been confounded by a decrease in acidity. Indeed, the various calcium saturations were achieved by mixing hydrogen-saturated clay, 3.7 pH, with calcium-saturated clay, 7.0 pH, thus giving clays a varying acidity. Using the same experimental system, Hutchins in 1936, who worked with Albrecht, reported that a treatment containing 0% calcium on the clay had a pH of 3.5, 25% calcium had a pH of 4.3, 50 had a pH of 5, 75% had 5.7, and 100% calcium on the clay had 6.9. And in other words, he wasn't measuring the pH in some of his early studies, and one of his colleagues, or maybe a student, had the pH of the clays that he was using and showed the pH was greatly different. And Albrecht wasn't measuring that. Another person measured that and said, hey, the pH differed. In another experiment conducted by Albrecht, calcium-saturated clay was mixed with barium-saturated clay. Here, the poor growth observed at low calcium saturation, which was high barium saturation, was probably due to barium toxicity. So here's another example of a potential flaw in his methodology. Okay? So they're saying that he was adjusting the calcium saturation. In this particular study, he used barium. And he said, oh, well, the calcium saturation definitely has an issue. It definitely affects growth. No, the barium toxicity was what was causing it. Albrecht's idea that plant growth is not limited by acidic conditions per se was explored again by Harston and Albrecht in 1942. Also using soybean, they concluded that since the soil pH at the beginning of the experiment was greater than 7, since the pH at the beginning of the experiment was up to 2 units higher than that at the end of the experiment, plants must be able to tolerate changes in pH, and hence soil acidity is not directly toxic to plants. I can't even say that as a soil scientist. I can't even say that sentence without laughing. It's so asinine. It boggles my mind how someone could be a soil scientist and say that soil pH doesn't affect plant growth. It's how is that possible? It's bizarre. But that's the mentality, that's the position of the person who was, credited with developing the base count saturation method. He didn't think soil pH affected plant growth, and you're following his method. It's insane. According to the Albrecht papers in 1975, Albrecht, 1939, demonstrated that for a balanced soil, 65% of the clay's capacity loaded with calcium, needs to be loaded with calcium, 15% with magnesium. It is unclear, however, how these balanced percentages were even derived. They don't even know. They just pull them out of thin air. The rate of N2 fixation measured as a difference of N content between the plant and the seed increased linearly with calcium saturation. The greatest fixation actually occurred at the highest rate of calcium saturation. So look down here. So this is his own data. Again, Dr. Albrecht's own data from 1939. They're saying that the calcium saturation needs to be 65%. Okay, that's what he's claiming. He was claiming back in 1975, I guess it was. 65% of the clay needs to be possessed. That CC needs to be possessed by calcium. That's what he's claiming. But his own data shows right here that maximum was achieved at greater than that limit, at 85% calcium. This is what his data show. It's in this zone. It's well above the calcium range suggested by Albrecht. So what these authors are saying, Kopetke and Menzies, are saying, we don't even know how they even came up with these ranges. They sure didn't come up with them from their own data. Because if you came up with your own data, you could make an argument right here that the range should be maybe 85, because that's where the maximum is. The maximum growth is, but they didn't do that. It's bizarre. No one knows how they came up with it. Similarly, the work of Albrecht in 1937 showed that both plants' mass and nodulation rate increased linearly with increased calcium saturation, which is what I just showed. Later, and notably after the work of Baer and Graham had been published, Albrecht stated that the extensive research project served up this working code for balanced plant nutrition. And then they have 10% hydrogen and calcium, 60 to 75%, and they have these various codes. While it is unclear as to the exact origins of Albrecht's balanced soil, it appears likely that it relied, at least to some extent, from Baer. What they're saying is they're actually pretty, professionally, they're quite assertive with their critique. What they're saying is, Albrecht said it was extensive work that we did to develop these ranges, but the ranges don't match his own data, and they actually look like they probably were pulled from Baer's work, not from Albrecht's work, because they don't match the ranges in his data. Whatever the exact origin or original purpose of the ideal soil, the base count saturation concept has subsequently been promoted widely, and many now consider that optimal plant growth will only occur when the soil contains the balanced or ideal cation ratio. The remainder of this review, we're going to talk about it from now on out. Okay, so now we're going to talk about, the author's going to talk about individual variables that the BS artists will tell you when they're trying to convince you to buy into base count saturation. Things like, we're going to increase the soil structure, we're going to increase the soil biology, and increase all these other things. They're going to talk about each one of those individually now, these authors. They're going to tackle each one of these. Soil chemical properties. According to the base count saturation concept, a balanced soil, calcium, magnesium, calcium, potassium, all these ratios, is required to ensure that plants produce both maximum quantity and quality. Thus, plant growth in a soil whose exchange complex is not balanced, does not contain the specific cation ratios, and may have reduced yields. So that's the argument from the BCSR wizards and warlocks and fraudsters. Toth, who had worked with Baer in the 1940s during the conception of the ideal soil approach, conducted an experiment investigating the growth of ladino clover. So this is a person who worked with him. It was concluded by Toth that provided calcium was the dominant cation, no specific cation ratio produced the best yield. Indeed, examination of the results showed that even when the exchange complex contained 40% potassium, or 40% magnesium, growth was no different to that obtained when the soil was ideal soil or when the soil was balanced. Okay, so let me show you what they're talking about right up here. So what he's talking about is the Toth work, which I believe this is Toth. Yeah, Giddens and Toth. This right here, what I'm looking at here is a bar graph. See, I don't know if I can get this on the screen clear, guys. My screen sometimes doesn't let me. Okay, here we go. What I'm looking at here is some bar graphs, and on the x-axis we have calcium to magnesium to potassium, and on the y-axis we have relative yield and percentage. And on the far right is the ideal soil balance, 65% calcium, 10% magnesium, and 5% potassium. This is what they would say would be ideal. And you can see when the ratios change, it can be 40% potassium, it can be 40% magnesium, it can be 25% calcium. The other values here are, there's no difference from them compared to the ideal soil. That's what they're saying. This is from a coworker of, or I guess a coworker, a student of Bayer. So you can adjust these ratios all over the place, and nothing differed from the relative dry weight of the plants when it was growing in the ideal soil. Okay, that's what he's saying. Okay, McLean, who had worked with Albrecht in Missouri during the 1940s, studied the effect of soil calcium-magnesium ratios on the growth of German millet and alfalfa. It was concluded that plant yields were not affected by calcium-magnesium ratios within the calcium-magnesium ranges that they studied. Similarly, Hunter in 1949, who had worked with Bayer in New Jersey during the early 1940s, investigated the influence of calcium-magnesium ratio on the yield of alfalfa, and Hunter concluded that there was no best calcium-magnesium ratio for optimum growth, figure 5. So figure 5 is down here, and this is y-axis of relative yield, x-axis is calcium-magnesium ratios. We have low phosphorus and high phosphorus, and what you're seeing is the relative dry weight was the same whether the calcium-magnesium ratio was very low or the calcium-magnesium was very high. It was flat line right across the top. Nothing changed. Okay, and this is from a coworker or a colleague of Dr. Was it Bayer? Was it Dr. Albrecht in Missouri? There is no difference. Change the calcium-magnesium ratio all over creation, and only in the most extreme, unnatural settings. It would never occur in nature, really. Only in those settings, and even really under those settings, sometimes we don't see any effect. But under those settings, sometimes we can see an effect when there's zero magnesium. You might see an effect. Well, the zero magnesium, not because it was unbalanced, just because there wasn't any available for the plant to uptake. Okay, that's what's throwing it off. Thus, it would appear that provided the soil contains adequate absolute quantities of calcium, magnesium, and potassium, the ratios of these cations generally do not influence plant yield within the ranges commonly found in soils. Therefore, total availability or supply is typically more important. Now, I skipped about 10 citations. I'm not going to read through this entire paragraph because all they do is go over one after the other articles over and over and over of from Australia to Virginia to you name it, going on corn, going on barley, wheat, going on canola, Western Australian no-tillage farmers. I mean, over and over and over, they show many publications that show the same thing, and that is you can change calcium, magnesium, you can have high calcium or low calcium, the ratio can change. What's important is how much is available or extractable according to the typical soil test method, and how much is likely to be available to the plant to uptake. Does the plant have enough or does it not have enough? We don't need to balance it off with some other element, okay? So we're going to continue. Besides yield, it has also been considered that under unbalanced conditions, plant quality may also be reduced. Indeed, Smith and Albrecht in 42 proposed that crops will be of lower nutritional value when grown in soils that do not contain balanced levels of soil. I mean, when the BS flows, it just flows freely from early indoctrinated and delusional people. Now, not only are you going to have reductions in yield, you're going to have reductions in quality, meaning the content of the actual plant itself is going to be reduced. Okay. And of course it doesn't. As discussed above, it was through this work that Albrecht concluded that acidity per se is not limiting to plant growth and that soils require a high calcium magnesium ratio. Interpretation of much of Albrecht's growth data is confounded by changes in pH. Plant growth is limited in acidic soil conditions, and the additions of calcium alone will not overcome the limitations imposed in such soils. So what they're saying is, if you have aluminum toxicity or manganese toxicity in low pH soils, applying gypsum is probably not going to help that much. You actually need to apply a lime, a calcium carbonate, to provide the calcium, but also to move the pH up. Okay, they're going to go over that. Studying soybean in acidic soils, Bruce in 1988 found that the addition of calcium by using gypsum or calcium chloride without a concurrent increase in pH typically had no effect on plant growth. In contrast, root length increased significantly when both pH and calcium concentrations were simultaneously increased. Indeed, there is extensive literature demonstrating the negative effect of acidic soils, particularly that caused by toxic levels of aluminum and manganese. So what they're saying is that there is a plethora of evidence refuting Albrecht's position that soil pH is not going to affect plant growth that much. Soil pH has an enormous effect on plant growth. Okay? And because he didn't believe it, he just disregarded it. It's not that important. What's important is the calcium saturation. It's just mind-boggling how this can continue from a scientist who would say that. I mean, if I stood up in front of any crowd and said, you know what, don't worry about soil pH at all. It's not going to affect the turf grass growth at all. Let's worry about the balancing. I would get thrown out of the room. I'd get laughed off the stage. Okay, he wrote this in his books. Dr. Albrecht wrote this in his books, and yet still people are convinced to follow his recommendations. It's just sad is what it is. In addition to the work investigating the growth and nodulation of legumes, Albrecht also investigated the effect of soil properties on the health and nutrition of grazing animals. I'm going to skip through the grazing animal part. He did a lot of ruminant animal work as well as soybean work. I'll just skip through it. So, several aspects of these studies by Albrecht are questionable. First, the observed increases in quality often corresponded to an increase in yield, thereby indicating that the reduced quality in the control was probably due to the presence of growth-limiting factors. Oh, my wife. Really? Oh, Lord. My wife just became a member. I don't know why she... Oh, okay. I guess you can become a member now. You can chat. That's true, Lou. You can do that. I had to turn off the chat to the... I had to switch the chat to members only. Which maybe I'll do that from now on, to be frank. I'll just do members only, and that'll be another perk for the members, is that for live chat, it's just members only. Unfortunately, we have a troll who comes in here occasionally and causes problems. So I'll just turn it to members only. Oh, you became a member on your cell. Okay, she told me that. Okay, well, I was wrong. Okay, we continue. Okay, the second problem was that although the addition of soil amendments increased quality, optimum application rates were not determined and the soil properties were not measured. Hence, the reported yield and quality increases cannot be ascribed with certainty to those conditions that were later promoted as balanced. In other words, we did this and we balanced the soil and we saw these results. Did you measure those soil nutritional levels? Well, no, we didn't. We didn't do that. Well, then how do you know? It's nuts. It's absolute madness how this information can still be perpetuated and promoted. It's just crazy, the amount of flaws and oversights that existed, the amount of indoctrinated positions that he held, the bizarre positions that pH doesn't affect plant growth. I mean, it's just nuts. Finally, although the addition of lime to move the soil closer to that considered balanced was expected to increase animal productivity through an improvement in plant quality, in some instances, the application of lime reduced animal live weight gains. I mean, it's crazy. He was doing this to increase the animal weight, and in some cases it reduced it. And he's like, no, it's working. It's crazy. Overliming has since been reported to reduce crop yield due to a deterioration of soil structure, reduction in phosphorus availability, and induced trace element deficiencies. Yeah, there's this belief sometimes in turfgrass management. I've actually seen this on YouTube. If I can find the video, I'll pull it up for Tuesday's show, where a gentleman's out there with some people in their lawn, and the people in the lawn are looking at him for recommendations. And you can see the guy's a complete BS artist. and he has a bag of lime, and he's saying, and the lady goes, well, how much should I apply? And he goes, oh, just keep applying it. You can't apply too much. And more is the better. No, that's completely wrong. You can over apply lime. Lime can be problematic. Okay. Lime can be very productive and very useful, but lime can also be a problem. Okay. And they state that right here by Eugene Camprath. Oh, Eugene Camprath. So he said overliming has since been reported to reduce crop yield. Eugene Camprath is my academic grandfather. He was the professor of my professor, and he published that in 1971. That's interesting. I didn't see that the first time through. Anyway, he published that overliming can be a problem. It can deteriorate soil structure, reduce phosphorus availability, and cause problems of micronutrient availability. Now let's talk about soil physical structures. This and soil biological issues are really the stomping grounds and the foundation of base count saturation BS artists. Companies develop huge. Their whole reputation is based upon this complete farce, is what it is. But let's see what they have to say about it. Soil physical properties. The balanced soil paradigm also postulates an effect on cation ratios on plant growth through changes in soil structure. In particular, surface crusting, compaction, and decreased hydraulic conductivity or movement of water through the soil. The high exchangeable calcium content of a balanced soil is undoubtedly beneficial in maintaining and improving soil structure and aggregate stability, for sure. The concern arises, however, that if the soil calcium content is lower and the magnesium is higher than that recommended by the BCSR, base count saturation, then soil structure may decline. This concern is based on the observation that soil aggregates 100% saturated with calcium are less likely to disperse than those saturated with magnesium. So in other words, in research, in the lab work, when they saturate the soil with 100% calcium, then they have issues holding it together sometimes relative to soils that have some magnesium in them. So they catch on to this little idea, and I don't know how it perpetuates. It gets perpetuated into our industry, and suddenly they say, no, magnesium's too high. It's gonna disperse the soil. Your soil is gonna be too compacted. You need to apply calcium to lower the magnesium levels on your clay. It's ridiculous. While a balanced soil is likely to have a good structure, however, this structure can be maintained across a wide range of calcium-magnesium ratios. For example, Rangasamy in 86 demonstrated that the structure of a red-brown earth was maintained across a wide variety of calcium-magnesium ratios, figure 7. So let's look at figure 7. What he's saying here is calcium-magnesium ratios on the X, relative hydraulic conductivities on the Y, and we're looking at increasing calcium-magnesium ratios. And what you see is that the hydraulic conductivity didn't change, whether it was 0.4 calcium-magnesium or 2.5 calcium-magnesium. Didn't change. Okay? So there's evidence, clear evidence in the literature to refute this soil physical property nonsense. And I hope people take that into consideration and don't let the BS artists and the fraudsters kind of convince you, I need to apply calcium because my magnesium's too high on the exchange sites and my soil's too compacted. That's a horrible, horrible argument. It's not supported by the evidence in the literature. Okay. I did that. Indeed, when soils contained low sodium concentrations, hydraulic conductivity was no different when there was twice as much magnesium as calcium. Twice as much magnesium as calcium. There was no difference in hydraulic conductivity to that when there was 2.5 times more calcium. No difference at all. It's the exact same. These laboratory observations of Rangasamy have been confirmed in the field. Schoenbeck in 2000, the poor hydraulic conductivity, crusting, and hard pans observed on these soils had often been attributed by the farmers to the cationic imbalance of the soil. Reductions in the magnesium saturation from 18 to 28 to 11 to 22, however, had no effect on the bulk density, moisture content, infiltration rate, or soil strength. In fact, the two soils that were the most unbalanced actually had the best physical properties. So what they're saying is that they went out and tested this in the lab. They went out and tested it in the field. They got a location where farmers swore up and down that it was compacted because of high magnesium, and they actually went out and measured it. And I bet you can bet the farm that if those researchers went out and measured out in the field and they indeed found that that was correct, that indeed lowering the magnesium actually did cause a result, a beneficial result, they would have published it too, and you would be sitting here talking about that. Indeed, it happened and it was correct, but that's not the case. We don't see that. Okay, we do not see it. I don't care how many observations you've made. I don't care how many thousands of acres of corn and soybeans you've grown. I don't care how many acres of turfgrass you've grown on quote unquote compacted soils, and how many times you put out calcium and gypsum or lime or whatever, and you've observed the soil become less compacted. I don't know how many times you've done it. There's no evidence to support it. Okay, they've gone out and measured it. It doesn't happen that way. Only in cases where there's basically no magnesium or no calcium, essentially, would you find the application of the other one to be beneficial. You see what I'm saying? So if the calcium was deficient, none, or magnesium was deficient, none, then adding that element would be beneficial. That's the Slan method. Okay? It doesn't matter. It's hard to, it's going to be difficult for someone to change their mind. There's a principle called Planck's principle. I was talking about that today. The people who are already convinced, they're probably never going to change their minds. Okay. But Planck's principle essentially says this: science and progression moves forward one funeral at a time. What that means is that the older people who are so convinced and they're the ones directing the industry, they're the leaders and the senior people who are, oftentimes people follow, they're holding the industry back, holding science back. They're holding it where they are. In order for science to move forward to the next level, the next generation has to come forward, and they need to be the leaders, and that's not going to happen until the next generation retires or dies off. And the reason I'm saying that is because the people who are convinced this is true, they're not going to change their mind. It's very, very, very difficult. Believe me, years of therapy talking here, okay? It takes a long, long time to change your behavior and your mental position on things. Okay, it takes serious dedication and work. They're not going to do that, especially when they're making a profit on it. But we can get the people in the middle who aren't yet quite convinced or aren't indoctrinated yet, aren't delusional yet. Those people who we can help. Okay. Now let's talk about soil biology and we'll be done. The provision of on soil biological activity, the provision of balanced cation ratios has been claimed to improve the soil biological activity and decrease weed growth and insect attack. Yeah, if it's not one thing and we shut that down, don't say, well, it increases soil biological activity and decreases weeds. And then we shut that down and they move the goalposts somewhere else. They're always shuffling the shell game, always moving the goalposts. And to be frank, we as scientists need to knock it off. We need to just stop chasing the tail because they have no evidence to support their position. There's none. So we just need to stop acting like, we need to investigate that. We need to do a study on that. No, we don't. It's been done. Stop doing it and just tell the stakeholders, stop listening to anybody who's giving you recommendations without providing any evidence to support it. Just stop. If they give you information, don't assume it's wrong, but go look it up. Go talk to a specialist. Confirm. See if there's any evidence. If there's not, then just discard it. Just forget about it. Go on to something else more important. Anyway, sorry. Nevertheless, in the trials of Schoenbeck 2000, a reduction in magnesium saturation from 18 to 11 had no detectable effect on soil organic matter, biological activities, abundance of weeds, or incidences of disease or insect pest damage compared with the controlled treatment. We don't have a lot of information on this, but what they're saying is the little information we do have doesn't show any benefit. Similarly, Kelling in 1996 concluded that the variation in the calcium-magnesium ratio had no significant effect on the earthworm population or on the growth of weeds, grassy weeds or broadleaf weeds. In the conclusion, I'm going to skip down to the red part in the conclusion. McLean, who worked with Albrecht in Missouri during the 1940s, stated that on the whole, there is no ideal basic cation saturation ratio or range. These are people who worked with these gentlemen. And that the emphasis should be placed on providing sufficient but not excessive levels of each basic cation rather than attempting to attain a favorable basic cation saturation ratio, which evidently does not exist. The data do not support the claims of base cation saturation ratio, and continued promotion of the base cation saturation ratio will result in the inefficient use of resources in agriculture and horticulture. And I would say inefficient use of resources and inefficient use of your money. And we're going to continue to go down this. We're going to look at, I've been going over basically review papers, which is what this was. I'm going to go into some of these more, the McLean paper, the Olson paper, some of Albrecht papers, Bear's papers. I'm going to go into those a little bit more, each one of them individually, so you have an idea. But I wanted to go over these papers first, so everybody kind of has an idea before we start. Because if you read the Albrecht papers and you didn't have any knowledge of how soil pH affects aluminum solubility or manganese solubility, or you didn't really have a firm understanding of that, then you would read the Albrecht papers and possibly read them and go, well, yeah, it sounds accurate. What he's saying sounds correct. And so I'm starting here and going over these papers first to explain how his papers were incorrect, how his conclusions were invalid, so that when we go and read those, we have a better understanding of, what is actually going on in his work. Same thing with Bear. Okay. So that's the paper for tonight. All right, guys and gals. Appreciate everybody working. I'm really sorry. I'm unable at the moment to include the subscribers in some of the chat. I can turn it back on real quick if you have a minute or two, or you have a second you want to ask a question. I'll turn it back on just as we get ready to say goodnight. If you have any last minute questions, you can throw it in the chat there real quick. If you're a subscriber, I turned it back on. Hopefully it'll work for the last couple of minutes. On Monday, I'll be back at 10 a.m. for the members only show. We'll be doing an article, and then on Tuesday morning, it'll be open to the public. We'll be doing a video, and then we'll be back again on next Thursday evening. Okay. Appreciate everybody showing up. Gray and Chuck and Ground Up Organic and Chuck says he could go for another hour and he would not be disappointed. I appreciate that, Chuck. I do. 99.9% of the people who watch this channel are very flattering and very, appreciative of what I do. And, it is, it's not for everybody. I get that. There's a couple here and there for some reason it's not their thing, and that's fine. What I watch on YouTube is not science related. It's other things. So it's not for everybody, but I do appreciate Andrew and, you guys, Eric showing up, Ground Up Organic, you guys, really appreciate it. And what I'll do is I'll leave you with some music tonight, and I'll be back on Monday morning. I really appreciate it, guys. Have a good evening. Have a good weekend. Bye.